Well, I think that to say outrageous, yes, thanks, Misha encouraged me, and I really say something probably very, how to say, that's bold, and my statement is, I will do two statements.
Only one outrageous statement.
Outrageous statement. But then some says in support of this outrageous statement. Some people say there is a classical part of differential geometry, which is a theory of surfaces, two-dimensional surfaces in three-dimensional space, and there is a theory of solitons in nonlinear wave theory, including the solitons in Cartevec-de Vries equation or solitons of in Kartasov-Petriashvili equation, three-wave equation. My statement is that all the theory of surfaces is a part of the theory of solitons. And now I add only two words. And you probably people heard about the classical problem of classification of three orthogonal coordinate systems. This problem was formulated in 1813 by Dupin and Binet, and the problem is how to describe the all three orthogonal coordinate systems in three-dimensional space. So, in other words, how to find the three functions, a set of three functions, u1 on x1, x2, x3, u2, x1, x2, x3, and u3, such that gradient ue, gradient ug is some h squared delta ag. And this problem was considered as one of the central in differential geometry, and Darboux in 10 years, 100 years after, in 1910, Darboux published a very thick book, a 600 pages book on this problem. And the central part of this problem is so-called Gauss-Lamé equations. I can write this equation, but probably it's not necessary. And my statement is that these equations are completely integrable by the inverse scattering method, and all these solutions can be found in the regular way. And this result is published by myself in the Duke, 1990. That's outrageous. Thank you. And the way how you describe, how you merge the theory of the surfaces in the theory of the soliton, that's a very natural way to merge any surface in the system of three orthogonal system. You just use a normal, and then I forgot how its transformation is known when you just, it's Lie transformation, yes, and Lie transformation. Then you construct a natural orthogonal system, and then by some reducing of this method, you can solve the Gauss-Kadatz equation. The Gauss-Kadatz equation is completely integrable system. This is my second statement. That's two-dimensional surfaces in three-dimensional. The same could be done for the surfaces in homogeneous in symmetric spaces.
Okay, for my outrage, but not sufficiently provocative, yeah. So, just somebody else want to volunteer, but otherwise I will nominate people, yeah. Invite Yasha, come here.
You will end your talk, which was talk.
Yeah, that one we really outraged, we lose our swim, what you say. If I start talking, we lose our swim in that sea. Yeah, so
You just cannot control your...
Yeah, because Yasha, the question which was asked about your talk, what is your thing where it goes? So you have this huge system of invariants in contact geometry. So what development is expected?
I'm just afraid it's not sufficiently outrageous for this discussion. Well, I don't know. So you see that the whole this kind of idea that, of course, kind of when we already was discussion about this today, that like from point of view of topology, what we want from all this kind of physical like construction, just to define some invariants, and also therefore kind of I was coming from this topological side, and so I was thinking in this term, but really this is probably and that's I still think that's kind of important question, and then in this part of the world, but kind of what I think that just this is some kind of universal structure which just exists by itself, and just kind of it's what I like about it, that it's kind of keep picture kind of keep all the time developing, and a lot of kind of other some everything kind of fits together in some in growing, and so just so it's just science. So it should be good for something maybe more serious than just counting invariants, but I don't know what it is.
But so the answer was expected. You have to say that contact geometry goes develop there, absorb all geometry, all physics, all mathematics, everybody about
Yes.
What do you expect of you? Why don't you say it?
No, but what do you expect?
No, but I was asking you. I don't tell what I think. Actually, I have somewhat this feeling, yeah, partly, that this is a structure which may absorb much of differential topology eventually. It has some edge which is, because it mixes geometry and topology. Now, in topology, only dimension 4 carries a long-term, dimension 3 carries trivial geometry. But symplectic and contact geometry have geometry and topology along.
Yes, so if just to speak kind of more generally, but of course not just what I was talking at this moment, but in general, then no, I think it's kind of it's too you of course you want outrageous statement, so it's of course then you should say that indeed would go this direction, but no. Okay, well I'm not prepared to outrageous.
Yeah.
Can I ask something as a physicist?
Yes, you come here, so you'll be heard. And so you'll expose yourself, yeah.
No, it's not me asking.
No.
So, I mean, there is this idea which I feel at least very partly responsible for, that non-commutative geometry and string theory should be logical twins. Now, one of the things that has sort of impeded implementation of the idea is that we don't know what Lorentzian non-commutative geometry is. And I would like to ask whether anybody has an idea of how it will look like.
Well, I think I will pass the microphone to my neighbor, Sergio, because I think Sergio has even more stronger opinion about this. So why don't you repeat what you told?
Well, actually, instead of answering, maybe I'll ask Misha a question. Why does why don't you consider Lorentzian geometry as being part of geometry?
Well, I do, but I just didn't come to that, yeah.
Well, okay, so why don't you say a few words?
Well, about Lorentzian geometry, I may say something which will be irrelevant for the kind of thing you do, yeah, because we don't have geometric, simple geometric terminology and language to speak about Lorentzian geometry. So apparently, in my view, you only can speak of very special Lorentz manifolds. There is no geometry of general Lorentz manifold. And I think you can give good justification for that.
But many of the most interesting objects in mathematics are special.
Well, but
Why do you look for generality? I mean, why don't you restrict?
Because I made this way. It's only because I made this way, and many other mathematicians made this way. We look for general principles, and I'm not saying you shouldn't look at that. Yeah, I'm saying you have to change the stand which we had in Riemannian geometry, where we could, in principle, say something meaningful about general Riemannian manifolds. Apparently, you cannot say anything meaningful about Lorentz manifolds. And this should be a theorem stated specifically why you couldn't do it, and essentially because Lorentz group is non-compact. Yeah, that's come from that. But I don't know exactly how to formulate it. Something similar to invariant theory. The space of the symmetric is kind of non-separable. Maybe you have to treat it immediately as non-commutative space. That's a possibility. It's more non-commutative in this sense, less separable than the space of Riemannian methods.
But what will take Lorentzian geometry to become part of geometry? I mean, most geometrists I know would exclude Lorentzian geometry as being part of geometry. I think it's...
Whom do you mean most?
Well, I'm not going to give names, but I talk to many people and they say, well, this is part of physics. It's not part of geometry.
No, but well, you have to give names, yeah? Then we can name by name just discuss it.
Well,
yeah?
even,
and again,
even you in a certain sense, even you told me that this is physics. It's not.
No, I can say it. Well, actually, I don't know what physics is, so I couldn't say it. The only thing, I repeat, it's very different from Riemannian geometry in spirit. And cannot be studied on the same principle. You have to change the stand, and it's unclear how to change it, but it's clearly you cannot study all Lorentzian manifold in a meaningful way. Yeah. That's what. That's
okay. I just wanted to say a few words. I only wanted to put you on the...
Yeah, sure.
But all I want to say is that, of course, Lorentzian geometry is not... The questions which will appear in Lorentzian geometry are not the same as the one we might expect in view of our experience with Riemannian geometry. But nevertheless, there is a Lorentzian world which is based on very simple geometric principles, in fact. I mean, it just happens to have arisen in special relativity, and it became part of physics. But at the same time, it's based on very, very simple geometric mathematical principles. It's a basic object, just like the basic objects you talked about at the beginning of your lecture. And I think it has been very little investigated in comparison with the other major structure in mathematics, which is Euclidean structure. So we have two fundamental structures, Euclidean and Lorentzian, and I think Lorentzian has been much, much less studied. But one should not expect that the questions which will arise will be the same as the one of Riemannian geometry.
Yes, exactly. I agree. They're different kind of questions. You don't know the questions. Yeah, that's what I'm saying. If you ask naive questions, extrapolate them from Riemannian geometry, they just don't work. Yeah, that's absolutely clear.
Yeah. Just a little anecdote. I'm not really an expert in this, but some years ago, Atiyah gave some lectures to mathematicians and physicists, and the first thing he said in the lectures was that he was going to analytically continue from the Lorentzian to the Euclidean metric. And what was interesting was the reaction of the audience. The audience, as I say, was roughly 50-50 mathematicians, physicists. The physicists all said, oh, yes, we do that. Yes, absolutely. All the mathematicians were completely outraged. They said, well, you can't do that. It's not positive definite. It's going to be completely different. So I don't know, maybe there's a cultural reason why we don't...
Yeah, I mean, this is quite true in the sense that at first, when you begin to look at quantum field theory and so on, you take this problem very seriously of actually working in Minkowski space and so on. But after a while, the physicists sort of convince you that you shouldn't take it seriously. And I mean, let me explain. I mean, there is one thing which is quite very rarely mentioned, which is that there is a framework of quantum gravity by Wheeler and De Witt and so on, in which the basic object is not space-time, but it is the space-like slices. And what happens then is that time only appears as a semi-classical variable. as a semi-classical parameter. So, I mean, they made a lot of work. They didn't succeed to construct quantum gravity. But they did understand one thing which is very striking, which is that, in fact, when we talk about Lorentzian geometry or about a Lorentzian space-time, we are imposing on ourselves the idea that there is a complete universe whose story has been written. And, I mean, this philosophically could be totally wrong. And, in fact, we could have a totally wrong idea about time. For instance, in my talk, I explained that time could very well appear just from non-commutativity and from quantum mechanics. I mean, from the lack of x, y, and yx. And we cannot, a priori, decide that we know that time is on the same footing as the other variables. I mean, I think philosophically this is a very delicate question. And to embark oneself, into a deliberate work on the Lorentzian side, I think before you really have to reflect to this basic problem, which is that we really don't understand the role of time somehow. And somehow physicists are extremely pragmatic people. So they decide that, if it's easier to do computations by putting an I, square root of -1, in front of t, okay, why not do it? And then you do it, you get formulas, and these formulas, they continue to work then. So then they're happy with it. And some people even take it as a fundamental thing. For instance, Hawking has this basic belief that the functional integral should be done in the Euclidean space-time matrix. And I mean, for many reasons, I mean, it has a lot of grounds, So somehow, okay, this question is, I think, completely open.
But Alain, just in case, we should also look at Lorentzian geometry on its own. Just in case that your picture is not right. No, I just, to make a point about this business of complexifying, you see, if you look at hyperbolic equations, which is the subject I know reasonably well, if you ask the question, what is a fundamental solution, then this analytic continuation makes perfect sense, because you can take the Euclidean case and just make exactly. So at that level, it works very well. However, if you really go deeper into the properties of wave equations, it makes no sense whatsoever. So, for example, you can ask simple questions like just very simple estimates for just the wave operator. And you say, like Strichhardt inequalities are a very good example. And you ask, can you derive them from the elliptic estimate? In the elliptic case, there are many more inequalities of this type which are forbidden in the hyperbolic case. And you can ask, well, can I prove Strichhardt inequalities from the corresponding elliptic estimates? The answer is, I don't know. I have no idea. I don't think anybody has any idea. And I think it's probably impossible.
Yeah, but what I would say, is that it might be we don't know now, but somehow, for instance, you see that causality translates into finite propagation speed. Exactly. So there are some things which do translate.
Yeah, but that has to do, they all have to do with a fundamental solution.
I would like to make one remark only. First of all, purely Lorentzian geometry does not exist. Yes, because you always have local Euclidean topology, so supposed to be some Riemannian metric invisibly present always. Also, first of all, but, yes, that's topology is dominated by some local Euclidean structure still, they say. Well, but my second point is following, that I would like just to inform you that some people with physics education who are present here certainly know that the possibility in quantum electrodynamics and in all interactions known now, the possibility to pass from Lorentzian to Euclidean geometry is experimentally confirmed highly. There is so-called CPT principle, which topological difference between them is that Lorentzian group has 4 connectivity components and Euclidean group has 2 connectivity components, and still behavior of all CPT theorem, CPT principle confirms that still everything is trivial if you are in one component from point of view of Euclidean geometry. So it is confirmed fact.
Yeah. It is true that if your space-time is Minkowski, then you can do this Wick rotation as Arthur at least described in his lecture. But of course, that's if we want to do gravity or so, Minkowski space is a little too limited, and we have no analogs of these theorems in general for general space-times, as far as I know.
Yes.
Yeah, let's just talk a little more down to earth here for a second. I think I agree with Sergio in the following sense, that it's more a result of style. If you take the theory of symmetric spaces that was mentioned a few times already, that's G mod K, where K is a maximal compact subgroup, and it's been studied probably mostly by Harishchandra. And I think his influence is such that that's what was studied for many, many years. However, recently it has become absolutely clear that all affine symmetric spaces are just as important. In the theory of automorphic forms, one now studies G over H, where H is the fixed point set of an involution. And the reason that was not studied primarily in America, in fact, only Japanese and Danish people studied this for some strange reason, is purely style. So I think I agree with Gromov that there are certain things in Riemannian geometry of the style that he does where it really is very difficult to imagine what the analog in the Lorentzian case is. But if you talk about harmonic maps or partial differential equations or wave maps, there are analogs. And the reason it's not studied in the Lorentzian case is style. People do what they feel comfortable. He was born to do Riemannian geometry first. The answer to Sergio is he must get up in his talk and try influence people to move in that direction by making interesting problems, and it's a matter of influence and style. It's not really intrinsic. In the case of affine symmetric spaces, no, but for certain problems it is not so different. So for affine symmetric spaces in general, it's true that the Riemannian case is easier, but in the end all the same theorems are true. Plancherel formula.
It's not an important point what you call geometry. Yeah.
Okay, well, it fits into my definition of geometry.
I just would like perhaps to turn discussion from physical geometry to geometry and ask you what a couple of directions you think is the most interesting in geometry now.
I refuse to answer that yet again. What? No, you cannot say just have to give two lectures. Two questions will be two lectures, yeah? You just cannot say it in one word, yeah? If you give such an answer, you have to give justification. This will be lecture.
No, but for couple, we still have 20 minutes, so...
The moment the gradient obviously lies in symplectic and fusion. It's symplectic and contact geometry. It's obviously where the gradient lies, yeah? So there's no question about that. That will be a gradient for the coming 10 years, yeah? I mean, no. Symplectic geometry and contact geometry certainly by far bypass Riemannian geometry, Lorentz geometry, and what we call geometry by far. So, and this will continue for at least for 2 decades. Yeah, that's obvious prediction. So what else can I say?
How do you see the future of this subject for the next 2 decades?
Well, I don't know. But you know, yes, some time ago I wrote an article. Symplectic geometry was called Part 1, and I still didn't write the Part 2 because I couldn't do it. Yeah, so I don't know. Because I didn't know what to do next. I couldn't do what I wanted to do, so how I can say about speak about it, I don't know.
It's the super manifolds is a lot of geometry.
No, but this is just terminology, it's emotional. It depends how you think about them.
Yeah, what do you...
Yeah, it's personally, who cares what I think personally, I mean. It goes on and that's it. But of course, it's again, geometry has several aspects to that, yeah? You can have something very algebraic and you call it geometry, it's fine, so it has a lot of geometric intuition. So you can make it so in wide sense or in narrow sense. Yes, and it becomes a question of terminology. Of course, in the wide sense, geometric intuition is used. In the narrow sense, it's not. So, and then it depends how you want to system. Yeah?
Well, you mentioned in your first lecture one problem that you think is not interesting, right? So that was the densest packing.
Yeah, exactly, densest packing, yeah.
So this, for example, is not interesting, or either is this not part of geometry, or this is not part of interesting geometry?
No, personally, just for me, it looked like historically problem which come from history, right? It was erased by Kepler. Just erase Kepler from the story, and the question would disappear. Like erase Fermat from Fermat theorem, and there would be no interest in Fermat theorem. And it's purely sociological phenomenon.
Well, it seems that in Fermat's theorem, the interest came also from the solution.
No, but it was by far before any before solutions. Yeah, there was some development influenced by that. But the focus on Fermat's theorem was due to the history, not the internal interest of the subject, right?
Yeah, but that's true for most mathematics.
No, it's not at all true, no.
From some history.
No, they come from the history, but the interest may be focused still on the internal. Like the Riemann hypothesis is unquestionably not because the Riemann raised it. Everybody believes it's a central problem. It's completely different. Nature is a very bad word. Nature meaning bad, exactly. Natural problem exactly those bad which arise without understanding them. Exactly. Natural problem is a bad problem. I agree with you. The natural problem means bad. Why? Because nature comes from uneducated mind. You know, people in the street ask natural questions. They're stupid questions. Deep question like Riemann hypothesis. That's an interesting question, of course. Nature is the bad word in mathematics. Exactly. Conceptually. Yeah. But now you want to say something.
Because Alain mentioned Hawking's book, I just don't know to what extent mathematicians are informed and follow what happens in cosmology. And it's true that about 20 years ago, it looked like the main problem there was a problem of the theorems, the singularity theorems. And therefore, when Hawking came up with the Hawking-Hartle boundary conditions, in which there was no beginning, because you go over to a Euclidean four-dimensional space, and then you add a point at infinity or something, and you close. You have an S4, and so in an S4 there's no origin, and the world doesn't. There's no beginning of time. But in the last 20 years, inflationary cosmology has taken over, because it has solved lots of other problems. And in that picture, not only has there been, in that picture really the universe is infinite in time. So the whole problem, this issue goes away. And on top of that, the singularity is not important because one has made calculations which have been published, very nice calculations, sometime with a tongue-in-cheek. For instance, there's a paper by Guth and collaborators, creation of a universe in the laboratory. And at least theoretically, we know how to make universes. And so in that picture, you have big bangs happening at distances perhaps of billions of light years, or of billions of light years, I don't know. But anyhow, the universe is then infinite. And so the whole issue of going Euclidean because of the singularities and the theorems of the singularities has gone away. So there's one less motivation for going Euclidean in that sense.
If possible, I will ask my second question. So you answer on the half of my question. Give one direction which you have interest. And I don't ask about second. I ask you now, please, if you may, to give couple of directions which are not interesting in geometry. You already said something on answering Noga question, but perhaps you may add. It's also very interesting.
Yeah, well, there were, I think, tremendous kind of confusion, not only in geometry, but in another branch of mathematics, when, for example, sociological factors were taking over. Or when people were mixing words, yeah, you just take the Riemannian manifold, there is topology, so I ask the question which I said in my lecture, what is topology, or which topology supports what kind of metric? This kind of question, very natural, very stupid questions. And that's exactly what we want to try to should avoid, yeah? We should avoid asking natural questions. So if you have a natural question, it says bad direction. So
what about quantum gravity? Is that a natural question?
Not at all. So ask a person in the street. He will come with this question, quantum gravity. Of course. Never. Exactly.
No, no, but somebody who knows quantum mechanics and who knows...
It's highly, it's highly...
knows that there is a contradiction between the two, and therefore...
No, it's a highly sophisticated question, yeah. It comes from deep thinking, in kind of conceptualizing this question, not from natural thinking. I don't want to make specifics, because if I will be concrete, I only can say I either have to invent stupid direction or what. Or I have to indicate direction which is stupid, it will be abrasive, yeah, I shouldn't say it. Yeah, exactly, yeah. You can count just everybody like that, yeah. Huh?
you regard the natural problem that you cannot solve as a bad direction, it's fairly ridiculous.
Yeah, I realize it's certainly outrageous opinion, but I think it's correct, yeah? Look at the natural world. Take all common opinion of people on any subject. It will be nonsensical, yeah? Yes, anything people think. Yes, behind how to go around obstructions, about astronomy, about physics, about chemistry, biology, life, everything's sheer nonsense, yeah? Okay. So-called folk wisdom. It's extension of folk wisdom. It's exactly what we have to shy away.
The natural question is not necessarily what a man in the street would ask.
No, a mathematician in the street. I mean, it's a man, I'm a mathematician. So if two people agree it's a good question, it means it's a bad question.
There is this thing from the introduction of Gary Larson's book, which basically says, what I'm asking is interesting, what you are asking is not. So, I mean, I'm willing to take this definition, but that's if we are trying to say something provocative. But I think, I mean, there are, so usually questions that has a long history.
Yeah.
I better not, right? No, I'm saying that usually a lot of the good questions are good questions because they have a history. So Fermat's last theorem was a good question because this created a great deal of algebraic number theory. And I don't know, the four-color theorem, although one may think that it's a stupid problem, this was one of the main reasons for the creation of graph theory and a great deal of combinatorics. So usually there are these questions that are natural, at least according to my definition, are natural, and are often indeed stupid questions, but still often they do lead to very serious mathematics.
I mean, the densest packing fields is more natural than the other question. This is a challenge that it's clearly there. Suddenly the asymptotic question in high dimensions. So if you think it's stupid, then solve it. I mean, or if no, it relates to very good mathematics. I mean, it's not clear.
It's hierarchy of questions, yeah. It's not,
what?
For me, this hierarchy of questions. Yeah.
But they're not.
For me, it lies very low. You say that the worst possible question of 3%, but there are infinitely many questions.
There are not so many questions, and it's not clear why it lies sort of this level. I mean,
it's not a low-level question from my point of view. There are infinitely better questions.
I will answer to you, and I will do compromise.
But about that
opinion. No. Point is that, of course, Misha wanted to say that things which are already obviously on the surface, and everyone understands what should be around, but we cannot yet prove. It's already in a sense, question of fashion of yesterday, which continue to today to be still considered to be fashionable. It's already of second interest. But not when you started to ask this question, not when Fermat invented this question, but perhaps when made development, which developed mathematics field. The same, not just a moment. Peter, Peter, let me to be more provocative. I just, then I will give you. You see, four-color problem was
I want you to talk here, so I want you to talk. I want to answer to Noga.
Yeah.
About this relevance of Fermat theorem to number theory, certainly nobody argues, and also the four-color theorem to graph theory, nobody argues, but there is a ready-made Russian tale exactly describing the situation. It's about the soldier coming to somebody's house and he's hungry, and the people of the house don't want to feed him, and he said, you know, I can make beautiful soup out of an X. Just give me metal X and I'll do the soup.
Stone soup. It's called stone soup.
It's called stone soup. Okay, you know the story. You know the story there, yeah? Okay.
I know.
Continue. Okay, so, and they were very much surprised and they want to know how to do it. You have to put this into the water and just boil it. And they're boiling, oh, it's going okay, but now we have to add, you know, some cabbage to that, just to make it better. And then you have to add some meat to that. And eventually come beautiful soup, yeah? And the same, exactly the same. Number theory was developing, and by the way, Kummer was very little concerned with Fermat theorem. It's a misconception. Yeah, it's conception in the popular books, by the way. I don't know about graph theory. Yeah, these are minor issues.
I think the one thing you haven't pointed out yet is the solution of Fermat's last theorem. Suppose some guy found a very easy proof which had used none of modern mathematics. It might have looked, you might contemplate that. What happened here is you might be complaining, as you did in your lecture, about the nature of the proof of how it was solved. You don't see it developing in new areas. that sense, he says, that's, I think, more of what you might complain about here than the problem itself.
No, but concerning specifically Fermat, there is a real theorem proven there, special case of the Langland's conjecture, and it's a reasonable achievement. No, but I want to say, this was development. Why we speak about Fermat? It was a minor kind of side effect of that, yeah? Yeah, it's side effect.
So he's saying that you care more about the solution than about the question.
No. Why? There was this fantastic question, Langland's conjecture. It was whatever, I don't know whose name conjecture it's called now. Tanyama way it used to be called. Yeah, that was a great question, and it stands as a great question. It's not a question somebody can ask. It's a very deep question based on understanding of the structure. And Fermat theorem will answer random question like 2 in square root of 2 equal irrational. Yeah, discussed with Don. It was a very stupid question. It's asked by Hilbert. It's a stupid question. Yeah, and the question you developed very well. But it was a stupid question. We had to admit it.
You said that it smells of a bad problem, yet it does seem to have a feature to it which stimulates good work.
Yeah, absolutely. That's quite possible. Yeah, that might happen. Yeah, I completely agree with that. Huh?
So you don't think that in mathematics there are sometimes these strange minutes when you say, oh, here is this question and we obviously should know the answer. I mean, it's so simple, it's so obvious. Yeah. And the fact that we don't know the answer says that we are missing something very important.
Okay, but it is not the case for maths.
No, we're talking about the densest. But the densest field packing belongs a little bit to this category.
Well, yeah, the table of Kepler was the case. Now the way you see the problem is still kind of rather...
Actually, about this particular problem, it since turned out that it's related to a lot of basic results in coding theory.
Okay, now I might be wrong, it may have some depth, and that's why I'm missing it, yeah? But on the surface of that...
Question, you see?
The densest sphere pattern.
In higher.
Okay. He will be the first to jump up and down.
Yeah,
I mean, why do you care about point
Are you complaining also about higher
dimensions?
What about higher dimensions?
Higher dimensions complain slightly. Because you see, when I was undergraduate, I was excited with this question because I knew no mathematics. This I couldn't understand. I thought it was great mathematics. And now I think it's second rate. I mean,
maybe you were right there in a long time.
Maybe we can possible to give a definition. Is it possible to give a definition of a good question as one which appears out of nothing at a certain moment because of some genius mathematician, but which is being immediately recognized as being very natural by everybody else?
Again,
is it natural?
Nature is a bad word.
No, but once a question is asked, maybe it's one can allow that everybody else.
Let me give a simple example. Yeah, is it natural for you when you're rotated, a stone then goes by straight line? Everybody learned to school, but most people still believe it goes by a circle. That's our natural belief, right? And just to say it goes along the straight line, no matter how we taught in certain situations, we behave as if it goes by a curved line.
How does it behave?
No, but I want to say that it's natural perception. Well, question or no question. It's now natural perception always deceives us, yeah? And there are experiments you can conduct with you, yeah? And you see, you just still believe you have a rudimentary belief coming from our kind of animal ancestors. Yeah? And the same in mathematics. And we should accept it and acknowledge that. Then we can make better questions. If we believe our feeling of naturality, we have some deep sense, whatever, it's absurd, yeah? We have to assume we are very stupid and our natural questions are stupid. And only by hard work, really conceptualizing, working hard, calculating, whatever, we can make good questions or good mathematics. And this naive, or we have intuition, something even stupid opinion. That's how I believe. You agree? Yeah? This is how we agree with me, yeah?
Can we, I mean, maybe if we, I mean, it's a shame to spend so much time on what sort of people feel are stupid questions. I mean, can I ask the question slightly differently? Where is geometry blocked?
That's a very natural question.
What? In other words, in any given, for example, in number theory, which I know rather better, I can point to 3 or 4 different directions that it's like a wall, that the subject is blocked. So I'm interested in your perception or experts' perception on where geometry is blocked.
Well, geometry is structure very different from number theory. It just doesn't go this way, spread, yeah? So there are some particularly difficult questions, and some of them are very good and natural, yeah? And we can solve them, that's for sure. But there is no one point where it's blocked. It was never like that. Geometry never goes far. It's like we can compare it to other branches of mathematics. It depends on a different part of your brain. Yeah, it's not consecutive part of the brain. We exercise long sequences. It's spread like visual perception. So it cannot be blocked. When you see something, you can't block. When you go, you are blocked. In geometry, you don't go ever.
Maybe number theory is blocked, but geometry is Gromov.
Okay. I would like to finish this discussion to ask another question, and I finish this on one compromise. Question has not the same value in time. When the four-color problem was invented, it helped a lot to mathematics. It was good. When it was solved, it was bad, and it was solved badly. Okay, so in any sense it's bad, and it may be on another discussion on mathematics in the real world or whatever you want. Because in fact, I did not finish yet.
I should answer in this case.
Yes?
Yes, you see, I would like to answer in this case about the solution is badly, yes? No, this is badly. I may tell you my personal opinion. The great topologist Haken, who started hyperbolic topology, in fact it was not later. The first one was started by Haken and solved important problem in pure topology. In particular, he found in particular that problem is not trivial, is algorithmically solvable. Yes, but he was immediately attacked by people that this algorithm are in sense of mathematical logic, you cannot realize them. You simply cannot realize them. That's so many operations. I cannot tell you what is P and P here, but that's no matter. But you have to input so many figures from the beginning that it is simply impossible to start with, really. And this great topologist made some in development, what people said badly, and many pure mathematicians are saying so, which is in fact much greater achievement, in my opinion, than any kind of people like beautifully solved like Fermat problem. It is in fact the logic of 21st century, which you even cannot control with such huge computing job. That is, you may think that it is ugly, but it is absolutely unique, yes? It was great achievement, and no proper credit for that is given in mathematics community, for example, in comparison with Fermat problem. So let me just, it was my just defendance of this great work. It was not badly solved. It was logic of future. Yes.
In fact, I agree with you. I agree with you completely. I think he didn't. I think it's actually Haken and Appel, is it?
Haken and Appel, yes.
Firstly, since you like to give credit to the right guy, you should get the name.
Right. Thank you very much.
I don't know about Appel, but Haken, I agree with you, was a great guy. I think one point that is coming up here, and it came up in your discussion, is, and I think this is going to be very relevant in the future, is the role of computers in proofs and in mathematics. And it doesn't seem to have been discussed. I think it's inevitable that computers will appear in the form of okay, sorry, I might not be. Okay. No, computers in proofs, not in science, not numerical analysis. I'm talking about the role of computers in pure math, in something like the proof of the four-color theorem, or the proof of the sphere packing problem.
I have a more radical opinion. I believe that maybe in 50 years mathematics will be less relevant than computers.
Well, that's
opinion.
I think if you want to think a bit about it, that's I think a very relevant question. So we can decide then.
You see, Peter, if Riemannian hypothesis would be solved with help with computer, I will consider this to be great achievement, because no matter how it will be solved. When you talk about four-color problem, the only interest which in such problem exists that if it is question so simple and we don't understand how to answer, then I would expect that some very young guy will find structure, will find missing structure here, and this structure will be more important to mathematics than four-color problem. And when you put 10,000 hours of computer just to say me that I will be able to find the right color, indeed I don't care. If it was developed some mathematics, this is the only thing which care. Problem is not solved well because someone killed good problem by 10,000 computer work. And this is what I want to say. So, but Now, I have, we still continue this subject, or I have another question to Gromov? I have more questions to Gromov.
Yeah, we can.
Well, I wanted to say that actually there was math going into it. I mean, it is. No, well, it's we just have to realize that there will be certain steps in proofs which is just not worth doing manually.
So it means the proof was not enough clever, structure was not
No.
something is missing.
No, not necessarily.
You're a man of
every proof.
Okay, also. No, I just want to say one word slightly different. It seems to me that kind of great breakthrough and some kind of great development happens when the subject not became yet very fashionable, and so it's quite. It seems to me that especially here in not here of course, but I mean where I am now in the States, that. Well, I mean, kind of in the West compared that as it was in Russia when, right. So, kind of extremely area become from time to time extremely fashionable, and then just everybody rushing there. And for instance, because of this, and then it's a kind of. But for instance, I feel kind of uncomfortable with what Misha said that about next 10, 20 years, the symplectic contact geometry will be this focus, and I really kind of already think that I should look for some place where somewhere to hide.
I must say that the problem of
natural that became not so good.
I must say that the problem of three orthogonal coordinates extremely fashionable in the last century and completely forgotten now.
I have, my first question is, it is 6 and 2 minutes. If you, I may provoke something else, but I don't know if someone wants to stay more. This is very serious. So perhaps to stop, I don't know. Good. Okay, no. Misha, then I had third question, because perhaps some geometry is not so great, not the best direction, and perhaps some bad geometry you don't want to mention. But what geometry is necessary to develop? Perhaps it's not the best, perhaps it's not the good, but what necessary to develop? It's another kind of...
I meet myself on the spot. You see, just in order to answer this question, I have to think, because committing myself. Yeah. For example, if you write proceeding for that, I can say write in proceedings. But this requires hours of thinking before you answer this question. Yeah.
Okay. So you will write this in proceeding. We have this written.
Yeah, written commitment, exactly. Yeah. But as you said, a conjecture is the most responsible thing you can do. Yeah. This, by the way, we can discuss because we have no room for that. What we spoke to Don another day, it's about conjectures. That. What is the meaning of the role of conjectures in mathematics? And sometimes people make conjectures when there is they have no right to make conjectures. Conjecture really comes hardly. You have to make conjecture, you can make it once or twice in your life. After deep thinking, and you just come up to a deep understanding, and you cannot finish it and make conjecture. You just cannot turn any question into conjecture.
How about punishment if you conjecture?
Yeah, exactly. This we can, and this exactly so it's very, very committing. To indicate direction and make conjectures. Do you have conjecture?